Hi all, this is my 7th lecture in probability, and in this lecture I'll be discussing something called the Gaussian distribution or normal distribution. Gaussian or normal distribution is a special case of binomial distribution, and the case is such that n is large and np is also large. If you remember what we discussed in lecture 6 on Poisson distribution, we saw that Poisson distribution is also a special case of binomial distribution, but there n was large, but the probability p was very small, so that np was a constant. But here n is also very large and np is also very large. When I say very large, they're so large that in the expression for binomial distribution function, we know that there is an n factorial, n minus m factorial, etc. So when n minus m, etc. are extremely large, the factorial terms can actually be replaced with Stirling's formula, which tells us that n factorial can be approximated as root of 2 pi n raised to n, e raised to minus n. If n factorial is like this, then m factorial would be like this, and n minus m factorial can be approximated as root of 2 pi n minus m. See, instead of n, you plug in n minus m. Instead of n raised to n, obviously you will have n minus m raised to n minus m. And instead of e raised to minus n, you will have e raised to minus of n minus m. Okay, since this is a special case of binomial distribution function, we start by taking the binomial distribution function itself, which is given by n factorial by n minus m factorial times m factorial p raised to m 1 minus p raised to n minus m. Okay, and instead of all these factorial notations, you plug in the expressions that you have written from Stirling's formula. Okay, when we substitute our f of m becomes like this, and rest of the terms I've left it untouched. So here I have all these terms. Now if you look at, there are many terms which can cancel as such. There is a root 2 pi, there is a root 2 pi in the denominator also, there is another root 2 pi also, let it be there. Then I have an e raised to minus n here, I have an e raised to minus n e raised to plus m, and here I have e raised to minus m. So the exponential terms, everything will cancel. Then I have an n raised to n, let it be like that. Then I have n minus m raised to n minus m, and I have an m raised to m. Okay, so I am just going to rearrange the terms. Let's see how it can be written. N raised to n, I write it as such. I had a p raised to m in the expression. See, here I have an m raised to m. So clubbing both these terms, I get p by m raised to m. Then I have a q raised to n minus m. Q, I have written it here as 1 minus p. We all know that q is 1 minus p. So q raised to n minus m. And here I have an n minus m raised to n minus m. So club both those terms. Now here this n raised to n is remaining isolated. So I just want to take that also within these terms. So here I have an n raised to n. What I do is I add and subtract an m. Okay. So this term would be n raised to n minus m plus m. So I have an n raised to n minus m which can go along with this term, and I have an n raised to m which can go along this term. So that's how I have obtained the step written here. Okay. The rest of terms within the root, of course, see from this expression, within the root I have n here in the numerator, n minus m in the denominator, m in the denominator, and a root 2 pi also. So this is my equation 1. Okay. Now I know that for a binomial distribution, m bar is np. This is the mean value. M bar is np, and let delta be the deviation of each random variable from the mean value. So delta is m minus m bar or m minus np. Okay. I also know that q is 1 minus p. So here in this expression for delta as m minus np, I am putting p as 1 minus q. Now open this, I get an expression like this, m minus n plus nq. So from here I can write an expression for n minus m as nq minus delta. I have n minus m here. I have an n minus m here. I have an n minus m here. Okay. For all these n minus m's, I am going to substitute nq minus delta. Okay. So that's what I have here. Okay. Now, similarly, my delta is m minus np, right? So m can be written as np plus delta. Okay. See, in this expression, I have m here, I have an m here, I have an m here. So for all those three m's, I am substituting np plus delta. So my expression for fm becomes like this. Okay. Now what do? I have np divided by np plus delta. Just invert this fraction. So my power becomes negative. And then I write my fraction like this, 1 plus delta by np. I can write it like that. Similarly, this fraction, 1 minus delta by nq with a negative power, nq minus delta. Now, within the root, just the same thing I am doing. Take np outside. When I take np outside this bracket, I get 1 plus delta by np. Now, I take nq outside. I have 1 minus delta by nq. So, I have an np and nq out of the bracket, and one n cancels with the n in the numerator, and I am left with these terms. Okay. Now, this term, root of 2 pi npq times 1 plus delta by np times 1 minus delta by nq. This I am putting it as some capital A, just for convenience sake. And I am taking this capital A to the LHS. So my LHS becomes Fm times A equal to this term times this term. That's what I have here. Okay. Now, see, simplifying this thing and to obtain an expression for Fm, it might be very difficult if we are working in this space. So for easiness, what I am doing is I am taking the logarithm on both sides. Okay. I am taking the logarithm on both sides. I get some expression, some simplified expression. Then what I do? I take the exponential on both sides. So I get an expression for Fm. It is like taking, say, suppose you have a problem in hand. You want to find a solution. Working in the present space would be extremely difficult. So what do? You transform it to some other space. See, by Fourier transform or Laplace transform, you are doing the same thing. Finding a solution to a particular problem in the existing variables might be difficult. So you transform that variable into some other space. You find the solution in that space, and then you take the inverse transform. You obtain the solution in the required space. Similarly, here also I need an expression for Fm. Directly finding it out using this expression would be very tedious. So what I do is, I take the logarithm on both sides. I get like this, right? This is something like a times b. So taking the log would be log a plus log b. But here, see, I have negative powers. So my expression will be like this. Okay. I hope this expression is clear. Now, just consider that the magnitude of deviation is much less than this npq. That's because NPQ, everything is extremely large. So the magnitude of delta is small compared to these values. So delta by NP is also much less than 1 and delta by NQ is also much less than 1. Then I can approximate, this will be a convergent series. This logarithmic series will be a convergent series, and I can write log of 1 plus delta by NP as delta by NP minus delta square by 2n square p square plus etc. So it will be a series with alternating plus and minus signs. And log 1 minus delta by NQ will be a series, the same type of terms, but except for the fact that all terms are negative. Now you substitute for the logarithmic terms in the previous expression, that is in equation 3. You substitute instead of log 1 plus delta by NP and log 1 minus delta by NQ as these terms. Okay, so you plug in these series there, and this is what you get. Okay, now all you need to do is you need to open the brackets. Okay, so the first term, just let's look at a couple of terms, we'll understand what we've written here. So minus NP times delta by NP, I'll get a minus delta. Minus delta times delta by NP, I get minus delta square by NP. Now the next term, minus NP times minus delta square by 2n square p square, I get a positive term. The second term is also a positive term coming out of delta, minus delta times minus delta square by 2n square p square. That will also be a positive term. The next two terms will be negative, like that. And you look here, minus NQ times minus delta by NQ. It will be a plus delta. Okay. Similarly, you open all the brackets, you will understand how these terms are coming. Okay. Now, this minus delta and plus delta will cancel. And remaining, I have minus delta square by NP. And here I have minus delta square by NQ. You club those things. And you club the remaining terms, you will get something like this. You just do it for yourselves and check what you are getting. You will get something like this: minus delta square by 2 npq minus delta cube times p square minus q square by 6 n square p square q square minus etc. Now since the magnitude of delta is very small compared to npq, there's no point in retaining higher delta power terms within this series, because all these terms are going to be extremely small. So you can just approximate this infinite series with the first term. You need retain only the first term because the magnitude of delta is very small compared to npq. Okay, so what do I have on my LHS? I have log fm times a. That will be approximately minus delta square by 2 npq. Okay. Now, what was my A? My A was root 2 pi npq times 1 plus delta by np times 1 minus delta by nq. But my delta by np is very small, it's much less than 1. Delta by nq is also much less than 1. So I can just approximate all these, this term to be 1 and this term also to be 1. So A can be approximated as root of 2 pi npq. So on my LHS, I have log fm times root 2 pi npq is approximately minus delta square by 2 npq. Now, I have a logarithm here. Now, how do I remove this logarithm? I take the exponential. Very easy. Now, when I take the exponential, I have fm times root 2 pi npq, and that root 2 pi npq I bring it here on the RHS, so I have it in the denominator. Then on the right hand side I had, what did I have? Minus delta square by 2 npq. When I take the exponential, that term will be like this. Okay, but I know my sigma is root of npq. So my expression turns out to be fm is 1 by root of 2 pi times sigma e raised to minus delta square by 2 sigma square. Okay. Now what is actually my delta? You can write it even like this. 1 by root 2 pi times sigma e raised to minus of. Now my delta was m minus m bar, right? M minus m bar square divided by 2 sigma square. This is the sort of expression that you would generally find in your textbooks for Gaussian distribution function. Okay. And this is a very useful distribution because almost all natural phenomena fit in this distribution, like age of people, height of people, the scores obtained in competitive exams like CAT, GMAT, etc. Everything fits in this distribution function. So it's quite a useful one in many natural phenomena. I hope you all understood the contents of this lecture. Thank you.